This is part 2 of lesson 8.4, finding area between two curves. This part of the lesson is going to pick up by looking at different situations that can happen when you're finding area under a curve. One of those is you might have multiple points of intersection. So what we'll have to do is break our area up into two pieces. So in the picture that you see here, what we have is we have a polynomial that we have a parabola, and then we have a cubic polynomial. So we have two sections where the graph intersects and forms an area between them. This first section that I'm highlighting, you'll notice that the parabola has the higher of the two y values, and then in the other section, the cubic polynomial is now above the parabola. So we have to break this up into two separate areas and then add them together. That's going to be the strategy. So f of x is 14x plus x squared minus 2x cubed, and g of x is x squared minus 4x. So we have to find the intersection first of the two curves. So I just want to we're going to call that A1 and the blue part A2. So we have two intersection points here. We have actually three. We have one here at -3. We have one at 0. And then we have one again here at 3. So it might be that you have a situation where you don't have the graph or the intersection points aren't that obvious. So what you want to remember that you need to do is you have to set your polynomials equal to each other and then solve for x to find those intersection points. Okay, so when we do this, we get 18x minus 2x cubed equals 0. Factoring out a negative 2x, we have x squared minus 9. So here are the three x's that we highlighted. We have x equals 0. We have x equals plus or minus 3. Okay, so now when we calculate the area, what we're going to do is we are going to take A1 plus A2, and that's going to equal the total area. Now you can write these together or you can write them separately. So you can first figure out A1. That's going to be the integral from -3 to 0, and the upper function is the quadratic. So you're going to have x squared minus 4x, and from that you're going to subtract the cubic function, which is 14x plus x squared minus 2x cubed dx. So we're going to go through and do that, and we're going to get, when we simplify this, we're going to get the integral from -3 to 0 of 2x to the third minus 18x dx. So A1 I don't know why this isn't writing, sorry. A1 is going to equal 1/2 x to the fourth minus 9x squared, evaluated between -3 and 0. So we're going to get the 0, 1 we can ignore, and then in parentheses we're going to have the minus there, so we have to be careful. So we're going to have 81 over 2 minus, and when we substitute -3 in the second term, we get 81. So that becomes 81 minus 81 over 2. So you get 81 over 2. Okay, now we need to do A2, and I don't have a lot of room here, so what I'm going to do is I'm going to slide the paper over, and I'm going to do it off to the side here. So A2 is going to equal the integral from 0 to 3. And now you have to put the cubic function on top. So that's going to be 14x plus x squared minus 2x cubed, and then minus the parabola, x squared minus 4x. And this is dx. And what we're going to see is we practically have the same integral. So when you simplify this, you get the integral from 0 to 3 of 18x minus 2x cubed. You have pretty much the same integral except the signs are the opposite. So you get 9x squared minus 1/2 x to the 4th. So when you substitute here, you're going to get the opposite, which is 81 minus 81 over 2. And so you get, again, 81 over 2. So then what we're going to do, sorry for the space, we're going to take A1 plus A2, and we're going to have 81 over 2 plus 81 over 2, which is 81. So there's our total area. Now you could have done that just adding the integrals together. You could have instead just done the integral from -3 to 0 of our first polynomial subtraction plus the integral from 0 to 3 of our other polynomial. And just to show the simplified one, the first one would have been 2x cubed minus 18x, and the second one would have been 18x minus 2x cubed. You could have done it that way, all in one step. Okay, next one. So sine and cosine curves obviously continue, and they want us to find just one region. And it doesn't matter because they're going to be the same no matter what. So when you have functions that are cyclic like this, you can find one region and then multiply the number of times that you need to find your answer. So in this case, we're just finding one. So I'm just going to use this region right here. And if I needed to find everything in a bigger region, I could just extend this, multiply by how many times it would cross over. So again, I'm going to need the graphs and decide which one is which is f and which is g. So the one on top, this, if you notice, goes through the x-axis. So that's going to be sine x. And the other one, which is below it, starts at a maximum, and when it crosses over here, it goes underneath it. So that's going to be my cosine graph. All right, now I need to know where sine equals cosine. And since if you look at the x-axis, I'm in the unit circle there. So sine and cosine are equal at 45-degree angles in the first quadrant and in the third quadrant. So my two x's are going to be pi over 4 and 5 pi over 4. And now I'm just going to integrate. So I'm going to integrate from pi over 4 to 5 pi over 4. And so I'm integrating sine x minus cosine x dx. So that's just going to be negative cosine x minus sine x, and that's integrated from pi over 4 to 5 pi over 4. So substituting, we're going to have the first one will give negative square root of 2 over 2, so that'll be positive square root of 2 over 2, plus, again, square root of 2 over 2, and then minus, substituting in pi over 4, we're going to get negative square root of 2 over 2 minus square root of 2 over 2. So simplifying, we get square root of 2 plus square root of 2, and that's just going to be 2 square root of 2. Now, if I wanted to add to it the next area here, the next area here, all I would have to do is just double this number because they'll all be the same area. Okay, so now looking at the graph, we're going to talk about using our accumulation process again. So we have a function that consists of a quarter circle and then 3 line segments. And it's defined from -1 to x, f of x. So the first thing we need to do is find f of -5. So we are going to do the integral from -1 to -5 of g of t dt. That will give me f of -5. So we're going to look at our areas here. Let me pull the picture down just a tad. Get rid of this. Okay, so we're looking at this triangle here and this triangle here, but they're going to cancel each other out because they're the exact same thing on opposite sides. So we really are just looking at the area under the quarter circle. So this integral becomes negative because I'm going to switch the limits of integration here. -5 to -1 of g of t dt. So that's going to equal -1/4, and that's going to be 2 squared times pi, and I'm going to get -pi. So that's the value at 5. So that's part A. I'm sorry. Part B says find all the values of x on the open interval, -5 to 4, where f is decreasing. Justify your answer. Okay, so let's start with the justification. Our justification is if we want to know where f is decreasing, that means that our derivative has to be less than 0. And remember that f prime of x is equal to g of t. So we're looking where g of t is less than 0. And that's going to be on the interval from -2, forgot that little piece, -2 to 1. Part C says, write the equation for the line tangent to the graph at x equals -1. I'm trying to juggle going back and forth between the graph. Okay, so at -1, we need the value of the function and the slope along here. So what you want to do is find the value of the function at -1 because that'll be the slope. So at -1, our function value right here is -2 because that's the derivative. And then if we were to integrate, I'm having issues with my laptop today, I apologize. If we integrate and find f of -1, we're going to integrate from -1 to -1 of g of t dt, and that's just going to be 0. Okay, so we have our point, we're at -1, 0. We have our slope, because f prime of -1 is going to equal g of -1, and that's equal to -2. So we can write our equation. Our equation is going to be y equals -2 times x plus 1. And then part D says find the minimum value of f on the closed interval, justify your answer. So here's where we're going to use our extreme value theorem. And we want to remember that the minimum, I should write absolute minimum. The absolute minimum occurs at the endpoints or a critical value. I'm going to run out of room again. Where f prime changes from negative to positive. Okay, so what I want to do is I want to make a little chart over here. I'm going to put it over here. And so I'm going to make a place where I can put all my, this is called my candidates test, all my points. So the endpoints are -5 and 4. And you notice I left one slot because there's only one critical value that meets that criteria of going from negative to positive, and that is here at 1, right here. Okay, so there's a critical value at 1, and that's the only place that it goes from negative to positive, which means that would be a minimum. The other one at -2 would be a maximum point because you're going from positive to negative. So my other critical number, or my only critical number that I'm looking at, is 1. So the values, we already found -5 to be negative pi. We'd have to compute 4 and at 1. So let's go ahead and do that on the graph. So at 1, we're going from -1 to 1. So we have this area here. We have a triangle. So it has a length of 2 and a height of 2. So the area is going to be 1/2, 2 times 2, which is 2, and it's negative because it's below the x-axis. So that value there is going to be -2. And then for 4, we're going from -1 to 4. So we already have from -1 to 1, so that's going to be -2. And then we just have to add on this triangle. This triangle has a height of 1 and a width of 3, so that's 3/2. So we're going to have -2 plus 3/2, which equals -1/2. So that's our last value of f. So there's -1/2. So the smallest value is going to be here at -5. Okay, so the minimum is at -5 with a value of -pi. Okay, and then finally, I'm going to leave the last problem for you guys to do. And this is actually kind of good after what we talked about recently, is that you have a calculator here and you have a not really straightforward integral to do. So you're trying to find the total number of cars on that stretch of the 10 miles. So you guys need to integrate from 0 to 10 of 180 times 4 minus the natural log of 2x plus 3 dx. So just put that in your calculator, and you should get 2,806 cars.